Okay, this video lecture will cover section 3.2, synthetic division. And so we'll begin here by discussing the division algorithm. Please fill in the blank on your note paper as we talk about this. Let f of x and g of x be polynomials with g of x of lesser degree than f of x and g of x of degree 1 or more. There exist unique polynomials q of x and r of x such that f of x equals g of x times q of x plus r of x, where either r of x equals 0 or the degree of r of x is less than the degree of g of x. Okay, and so this is important here. Make sure that you kind of make note of this, and this will make a lot more sense as we get to an example where we actually have some missing terms, but keep this in mind to avoid errors. Use 0 as the coefficient for any missing terms, including a missing constant when setting up the division. And so, as I said, when we get to an example where we actually have some missing terms, I will really point this out, but we want to keep this in mind in order for you not to make a mistake on your synthetic division. Okay, let's look at example 1, using synthetic division. And so we're going to use synthetic division to divide 5x cubed minus 6x squared minus 28x minus 2, divide that by x plus 2. So I'm going to start with what I call what goes outside the house, so to speak. And so I take my denominator, what I'm dividing by, the binomial x plus 2, and I know that I need to do opposite sign outside of the house when it's given to me as a binomial, like x plus 2. So in other words, I'm going to put negative 2 outside the house, so to speak. Okay, and the next part goes back to this. I'm going to check for any missing terms. And I look at my powers of x. They should be in descending order. And there should be no what I call skips. Okay, in other words, there should not be anything missing. And so let's check that. I have x cubed, then x squared. This is x to the first. And my constant term here is understood to be the coefficient of x to the 0. So they're all in order, 3, 2, 1, understood to be x to the 0. I don't have any missing terms or what I refer to as skips. So I can put these coefficients inside the house here in the order that they are and not have to fill in any zeros. Okay, so I'm going to put my 5, then my negative 6, then my negative 28, then my negative 2. And I always, when I'm doing synthetic division, I bring down this first number that's inside of the house. Okay, next step is I multiply. Negative 2 times positive 5 gives me negative 10. Then I combine these by using my sign rule. So if signs are the same, I add and keep the same sign. Negative 6 and negative 10 gives me negative 16. Then I multiply again. Negative 2 times negative 16 gives me positive 32. Signs are different, so I subtract and keep the sign of the larger number. Negative 28 plus 32 gives me positive 4. And then I multiply again. Negative 2 times positive 4 gives me negative 8. And then again combine. Signs are the same, so I add and keep the same sign. Negative 2 plus negative 8 gives me negative 10. And this last number here is always your remainder, okay? So that is not, we're not done with the problem. That is not how we give our final answer. So the final answer will be given as a polynomial. And so I go back to my problem and my numerator here, or what I was dividing into, the highest coefficient was x to the third. So that means here, the result I got when I did my synthetic division, this is now the coefficient of one less exponent than what I started with. In other words, if I started with x to the third, then I know this is the coefficient of x to the second, x squared, minus 16x plus 4, and then we'll talk about what to do with the remainder. So my final answer will be given as 5x squared minus 16x plus 4 plus, and then I will have negative 10 over what I was dividing by. And remember, we were dividing by x plus 2. And so this is how I would give my final answer for this problem. Okay, let's move on to example 2. Okay, and so now we're going to talk about the remainder theorem. Okay, evaluating polynomial functions using the remainder theorem. And the remainder theorem says if the polynomial f of x is divided by x minus k, then the remainder is equal to f of k. And so in more plain terms, what this means is that if I divide by x minus k, then the remainder is basically my answer here. In other words, it's the same thing as if I plugged this number back into the function and worked it out. So instead of having to go through that, I can use synthetic division to find f of k. Alright, so let's apply this to example 2, and I'm going to put this on another sheet of paper so we have more room. Okay, so example 2 says let f of x equal negative x to the 4th plus 3x squared minus 4x minus 5. Use the remainder theorem to find f of negative 3. Okay, notice that we're wanting to find f of negative 3. And so what this remainder theorem allows me to do, rather than having to plug negative 3 back in for x and work that out, is I'm going to use synthetic division instead to find f of negative 3. So this time, since they're giving me f of negative 3, I'm going to actually put negative 3 outside the house. Notice that I didn't do the opposite sign here like I did on example 1. That was because we were dividing and they were giving me the binomial to divide by there. Here where they're saying find f of negative 3, so I simply put negative 3 outside the house. Okay, inside the house will go my coefficients. And so if we take a look at this particular function, we see that we do have some missing terms. We have negative x to the 4th, then we skip x cubed, then we have x squared, x to the 1st, and finally this would be understood to be the coefficient of x to the 0. So right here in between these two, and you might want to even write it up above, that I'm going to have 0x to the 3rd, and so that coefficient 0 has to be put in between these two coefficients, okay, because I'm missing that x to the 3rd term. So understood to be in front of x to the 4th would be a negative 1, so I'm going to put that first. Then put your 0 for the missing term. Then put your positive 3, then your negative 4, then your negative 5, okay? And so I kind of go back and say, okay, that's 4th, 3rd, 2nd, 1st, my constant. And I always, just like on the previous problem, simply bring down this first number, okay? So now I'm going to do that same process we did on example 1. I'm going to multiply negative 3 times negative 1 would be positive 3. 0 plus 3 would be 3. Then I multiply. Negative 3 times positive 3 would be negative 9. 3 minus 9 would be negative 6. Negative 3 times negative 6 would be positive 18. Negative 4 plus 18 would be positive 14. And negative 3 times 14 would be negative 42. And then negative 5 plus negative 42, we would add because signs are the same, and we get negative 47. And remember, this last number is always our remainder. And for this particular problem, because we're using this remainder theorem, then we can say, it told us to find f of negative 3, that f of negative 3 is whatever I get when I do my synthetic division. It's whatever I get for my remainder. So to answer the question, f of negative 3 would equal negative 47. My remainder is my answer here. Okay, so the next thing that we want to look at is testing potential zeros. And it says a zero of a polynomial function, f of x, is a number k such that f of k equals 0. Okay? The real number zeros are x-intercepts of the graph of the function. And so what this really means is that if I perform my synthetic division and I get a remainder of 0, then that means that given number is a 0, or in other words, an x-intercept of the graph of the function. Okay, and this will make more sense as we work through the example. So let's look at example 3, deciding whether a number is a 0. Okay, so we're going to determine whether the given number k is a 0 of f of x. Okay? And so here they're giving me on the end f of x is equal to x cubed minus 4x squared plus 9x minus 6. And on the end here they say k equals 1. So in other words, this is the number that we're testing to see whether it is a 0, or in other words, keep this in mind, an x-intercept of this graph of this function. So again, I'm going to put this number, since they're giving it to me as k equals and not as a binomial like x plus 2 or x minus 1, since they're giving it to me as k equals, I'm simply going to keep it the way it is and put positive 1 outside the house. Okay, then I look back at my polynomial and I check for those skips, those missing terms. Well, I have x to the third, x squared, x to the first. This is understood to be the coefficient of x to the 0. I have no missing terms, no skips. So I can put my coefficients inside my house just the way that they are. So that would be understood to be a positive 1 in front of x cubed, negative 4 would go next, positive 9, and then finally negative 6. And I'm going to bring down this first number. Then I multiply. 1 times 1 is 1. Negative 4 plus 1, I subtract and keep the sign of the larger number. 1 times negative 3 is negative 3. 9 minus 3 is 6. Then I multiply. 1 times 6 is 6. And negative 6 plus 6 is 0. And again, this last number here is always our remainder. And since our remainder is 0, then we can answer that yes, this k equals 1 is a 0 of this polynomial. Okay, and the reason again that we can answer yes is because the remainder here, when we did our synthetic division, was 0. Okay, so we'll move on to the next example. Still the same thing. And so on B here, we're given the function f of x equals x to the 4th plus x squared minus 3x plus 1. And this time we're testing k equals negative 1. In other words, we want to know, is negative 1 a 0 of this polynomial, an x-intercept of this polynomial? So again, since they give me this on the end, k equals negative 1, I will put negative 1 outside the house. Okay, so inside the house will go my coefficients, but always remember to check for those missing terms, those skips that I called them. So I have x to the 4th, then I skip x to the 3rd, I have x squared, x to the 1st, then my constant term. So here in between these two, I need to remember to put a 0 here for my missing term x to the 3rd. So we'll start off here. Our understood coefficient here is positive 1. Then I put my 0, then another positive 1, then negative 3, then positive 1. And I bring down this first number. Okay, same process as before. I multiply. Negative 1 times 1 is negative 1. 0 minus 1 is negative 1. Negative 1 times negative 1 is positive 1. 1 plus 1 would give me 2. Then multiply. Negative 1 times 2 is negative 2. Negative 3 plus negative 2 gives me negative 5. Negative 1 times negative 5 gives me positive 5. 1 plus 5 is 6. And again, this is my remainder. Well, this time we did not get a remainder of 0. And because of that, since our remainder is not 0, then we have to answer no here. No, k equals negative 1 is not a 0. Okay, moving on to our last example for this section. We're still again using the same instructions. We're deciding if this is a 0 of this given polynomial. So notice what we're given here for our k. K equals, and it's a complex number, 1 plus 2i. And so that is what we're going to actually put outside of the house, is 1 plus 2i. And then inside the house will still go my coefficients of my function, of my polynomial. So let's check for those missing terms first. Always check for that first before you put anything inside of your house. So 4, 3, x to the 4th, x to the 3rd, x squared, x to the 1st, my constant term. I don't have any skips this time, so I can simply put my coefficients in and not have to put in any zeros. So I have positive 1 here, negative 2, positive 4, positive 2, and finally negative 5. And I want to bring down this first number. Same process. Okay, so I'm going to multiply, and I'm going to put that in parentheses. 1 plus 2i times 1 would be 1 plus 2i. Notice that I'm lining up the real number part under the real number, okay? And that's how you need to keep it. And so now I combine the real number part, negative 2 plus 1 would give me negative 1, and I bring down my plus 2i. Okay, so again, I'm going to multiply just the same process we've been doing, 1 plus 2i times, and I'm going to put parentheses around this, negative 1 plus 2i. And so from a previous lesson, you probably have learned that you may use your calculator to help you multiply these complex numbers. And so if I use my calculator to multiply this, I'm multiplying 1 plus 2i times negative 1 plus 2i. I will type that in, and I'll do parentheses, my 1 plus 2i. To get your I, you do second decimal point, close it, and then just open parentheses because we're multiplying that times this. So parentheses, and you have to use your negative key here for this negative 1, not your minus key. Negative 1 plus 2 second decimal point, close it, and enter. And it tells me that that gives me negative 5. And probably I should have honestly left a little more room here, but continuing on, I have 4 minus 5, which if I subtract, that gives me negative 1. Okay? So now I'm going to multiply 1 plus 2i times negative 1. Well, again, if you want to use your calculator, you could, but that's just going to give me, if I do distributive property, negative 1 minus 2i. And again, always when you have a complex number, line up the real number parts, this real number here with the real number part below it here, and put the I part second always. Okay, keep this lined up. That's important. So 2 minus I gives me positive 1, and then I bring down my minus 2i. And then now I'm going to put this in parentheses because I've got to multiply 1 plus 2i times 1 minus 2i. So again, I'm going to use my calculator to multiply those complex numbers. So I do parentheses, 1 plus 2 second decimal point, close it, and then times. So I'm just going to open parentheses, and I'm going to do 1 minus 2 second decimal point, close it, and enter. And it gives me positive 5, and that goes up under here. So negative 5 plus 5 gives me a remainder of 0. And so I can answer, remember our original question was, is this a given 0 of this polynomial? And since our remainder is 0, then the answer is yes, it is a 0 of this polynomial. Okay, so practice on your own. Exercises 3, 7, 29, 45, and 53 on pages 305 to 306 in your textbook. Those are odd, so you can check those in the back of your textbook, and if you have any problems with them, then you need to ask your instructor about those to help you.